Let's take the derivative of the tangent of arc secant of AX. First, let's draw ourselves a right triangle to help sort out what these trigonometric functions mean. Remember that arc secant is a function which turns a hypotenuse over adjacent side of a right triangle into an angle. We'll call that angle theta. Let's put that angle here. And that tangent is equal to, well, a tangent is a function that turns an angle, and in this case it's our theta, into an opposite side over an adjacent side. So since arcsecant of AX, since we're taking the arcsecant of AX and arcsecant takes a hypotenuse over adjacent and turns it into an angle, that means that hypotenuse over adjacent is equal to AX. So it would be convenient to say hypotenuse is equal to AX and adjacent side is equal to 1, because that meets our needs for this arcsecant that we're going to take. So we could say arcsecant is AX, hypotenuse is AX, and adjacent is equal to 1. That actually doesn't work out for us in this case because the hypotenuse of a reference triangle is always going to be an absolute value. When we created this reference triangle, we're actually implicitly defining it as a set of vectors where we have the adjacent side is in the I direction, the opposite side is in the j direction, and the hypotenuse is just a scalar distance. It has no direction. It's a scalar distance between the origin and the addition of these opposite and adjacent vectors. If we wanted to give it direction, we'd have to use theta to do that. But as it is just a value, it does not have a direction, and so like it doesn't matter if we're moving in the negative x direction or moving in the negative I or the negative j direction. The distance between 2 points is always going to be positive. Negative distance isn't something that we consider in this kind of geometry. So AX isn't going to work for us in the hypotenuse because sometimes x is going to be negative, and we need to know when our function is moving in the negative direction, and we're going to need to take account of it, because if we do this, it'll be as is. If we continue going down this road, all the positive values will work, but look, if x is negative here, then the absolute value signs are going to negate that, and we're going to misread that as a positive, and our final derivative will only be true for positive values. So another way that we can write this same exact thing is 1 over, so we have hypotenuse of 1, and adjacent side is 1 over AX. And then, if you multiply by the reciprocal of the denominator, then you would it's the same thing as saying AX. So if we say 1 over 1 hypotenuse and 1 over AX is the adjacent side, that actually meets our needs because the absolute value of 1 is 1, and since this vector has both distance and direction, then the negative values of the x are taken into account like I said, for negative values. It's not just going to be true for positive values. And we're going to want to solve for the adjacent side now. We can use the Pythagorean theorem. So opposite squared plus adjacent squared equals hypotenuse squared. we're solving for hypotenuse, so we can leave that alone. Adjacent squared. Adjacent is equal to 1 over ax, so we have 1 over ax squared, which is equal to 1 over a squared x squared, and that's going to equal the hypotenuse squared, and hypotenuse is 1, so squared, and that's equal to just 1. We can subtract 1 over a squared x squared from both sides, and let's go ahead and bring this over. We get opposite square equals 1 minus 1 over a squared x squared. Take the square root of both sides. And we're taking the principal root for the same reason that we didn't want anything in the hypotenuse. The principal root gives us the positive distance. Since negative distance doesn't mean anything, the x's can be negative, and that just denotes a negative, it means you're moving a positive direction in a positive distance in a negative direction. So it's absolutely fine to take the principal square root. We don't care about the negative root because that's talking about a negative distance. So we have the opposite side is equal to the square root of 1 minus 1 over a squared x squared. So moving on, we have arcsecant of x, which we have defined as theta. So we have y equals tangent of, replace arcsecant of x with theta, and then tangent of theta is equal to opposite side, which is square root of 1 minus 1 over a squared x squared over 1 over ax. We can multiply the numerator by the reciprocal of the denominator. We get ax times the square root of 1 minus 1 over a squared x squared. So now we'll take the derivative of both sides with respect to x, and we get the derivative y equals the derivative of ax times the square root of 1 minus 1 over a squared x squared. And since a is a constant, we can write that out in front. We can draw that out of the derivative that we're taking and multiply it. That's just a scalar value. Clean this up a bit. And looks like we have x times, we have a function times a function. We have x times this square root function. So we can rewrite this all yet again as, you know what? This is actually going to be more convenient to take with the a on the inside in this case. So let's leave it in there. And we're going to split this up as ax as a function and this stuff under the square root is a function. So we have the derivative of y equals, using product rule, we get derivative of ax times, and I'll just copy this so I don't have to keep writing it. So the derivative of ax times square root of 1 minus 1 over a squared x squared plus ax times the derivative square root of 1 minus 1 over a squared x squared. And let's, it'll be more convenient to write this square root as an exponent. So the square root of something is the same as saying the 1/2 exponent. And let's start, we can start taking the derivative now. So the derivative of y equals, derivative of ax is going to be equal to a times our square root function here. And we're going to add ax times, now we need to take this derivative. It'll be a little bit involved, so instead of doing it over there, let's just create a new space to do it. Copy this, bring it over here so we can work on it. The derivative of all this is nested within the 1/2 the square root function, so we can move towards using chain rule. Let's say u equals 1 minus 1 over a squared times x squared. And now dx of u to the 1/2 power, and we can use chain rule here, so we'll say du dx times du, and then the derivative of u with respect to x is going to be du dx is going to be equal to the derivative of 1 is going to be 0 minus the derivative of, let's rewrite this as ax to the negative 2, and then, well, is that the most convenient way to take it? We can actually we'll draw the a out, so we have 1 over a squared times x to the negative 2, and that way we won't have to use another chain rule, so we can just draw out 1 over a squared and multiply that by the derivative of x to the negative 2 is going to be negative 2 times x to the negative 3, which is the same thing as 2 over x to the third and we're going to get a negative times a negative, which is a positive, so we can get rid of these negative signs, and the 0, because the 0 doesn't do anything, and that's going to be 2 over a squared x to the third. 2 over a squared x to the third. So we can write that here. Du dx is equal to 2 over, just copy and paste that, 2 over a squared x to the third. Actually, I'm going to fix that a because it looks like a 9, times the derivative of u to the 1/2 is going to be 1/2 times u to the negative 1/2, which is the same as 1 over 2 times the square root of u. And undoing the u substitution, we get 2 times the square root of 1 minus 1 over a squared x squared, because we just replaced the u value from up here. These 2's are going to cancel out. Left with 1. And we can multiply the denominators together. There we go. Center R1. And that is our d dx of this function. So let's bring that over. And it looks like we'll have this a cancel with one of these a's because we're multiplying. Let me make it a little clearer here, this multiplication sign. And one of these x's will cancel with one of these x's. So we're left with a times x squared in the denominator here. And get rid of this. Bring this over. And let's see, is there anything else we'd like to do here? Looks like we can simplify this a little bit further by giving like denominators and completing this addition. So we'll start off with the ax squared. We can turn this into a squared, and then of course get the x squared as well. So a squared x squared times the square root of 1 minus 1 over a squared x squared. We have that factors in the numerator as well, so we can get rid of that square root symbol. Bring in some parentheses. Let's get these on the same level. So now that we have like denominators, we can combine the numerators. So let's get rid of this. Extend this out and add the plus 1 we had. Give ourselves a little more room to work. And if we multiply a squared x squared times 1, we get a squared x squared, and then minus a squared x squared times 1 over a squared x squared is going to be equal to 1. So we get a squared x squared minus 1 plus 1, but the minus 1 and plus 1 cancel out. Then we have one of this a will cancel out one of these a's. This x squared cancels out with this x squared. So let's take care of that. Center our a. And we are done.